So now in a separate video, I will go over these other growth rates. We have specifically the exponential time and the factorial time. All right, and notice that basically how these kind of rank. A logarithmic algorithm grows pretty quickly at first, and then it gets slowed. Logarithmic algorithms are great. We'll go over them later, but essentially, whenever each step you take halves the amount of work you're doing, you're in a logarithmic condition. Linear, that grows like a line. Log linear almost grows like a line, but speeds up just a bit because it's this times this. Quadratic goes up, but it doesn't go up nearly as fast as cubic or exponential. An exponential algorithm is where the n is not the base, it's the exponent instead. Right? And we see that essentially that the effects of these growth rates are huge, right? If we are dealing with 50 items over here, right? O of n means we've got 50 units of work. If we've got 100 items, that means we're doing 100 items of work. Where for n squared, we're doing 2,500 versus 10,000. Huge jump over here. And the jumps get utterly massive here and here. It's a bit hard to comprehend how massive these jumps are because it's like 15 to 30, that's not that much. That's 15 zeros and then 15 more zeros. All right. So to give a better idea, algorithms with exponential and factorial growth rates, there's a size limit where basically there's an effective practical limit on the size that they can be used to solve. It used to be said, the slides, one of the mistakes in there that said that they could not be solved. That basically meant it could not be solved. And the answer is, that's kind of true. Once you get these problems big enough, the universe will die before the problem can be solved. The universe will end. All the stars will blink out, and the problem will still not be solved, essentially. That's how long these exponential or factorial problems can take once they hit an appropriate size. So if you have an exponential algorithm, if 100 inputs take an hour, then solving it on 101 inputs takes 2 hours. 105 inputs takes 32 hours, right? It doubled, then we doubled it, and so on. And then 114 takes 16,384 hours, almost 2 years. Now, I'm kind of getting this out. I like this, like it sounds like it's a good thing, and it is a great thing because this ties into encryption, right? If you care about your security, then our encryption algorithms, our cryptographic algorithms, they can be broken by brute force, right? They can crack they can come up with an algorithm that will crack your password open like a clam. The issue is that these are some really tough clams if it's done properly, right? Some cryptographic algorithms can be broken. It takes exponential time to crack these passwords, right? Where n is the number of bits in the key, numbers and ones and zeros in there. A key length of 40 used to be good decades ago, but you can break a key length something with 40 bits. But 100 bits takes a billion times longer. It takes ridiculously long. So something with like 2048 bits for your encryption key, you're not going to be able to break that unless as you learn in the algorithms class, somebody comes up with a quick way to factor out your primes. All right, so these problems take forever to solve, and that's sometimes a good thing, as I've just said here. This means that it's really hard to crack your password by brute force. Okay. Another example of a problem of one of these problems I'd like to go over is the traveling salesperson problem. And this one is basically, say we have 5 cities, right? We have 5 cities here, right? These are 5 major cities. Here we have the nice and prosperous city A. You have the less prosperous but still major city B and C. Whoops. C, D, and E, right? So we've got these 5 cities here, and suppose you're a salesman selling widgets, right? Okay, and your home base is maybe here, or whatever. It doesn't really matter for the purposes of the problem. You're gonna go, and you've got clients in each of these major cities, all right? Now each of these cities are major hubs meaning they have an airport, so you can fly to each of these cities from one city to any other city because of the wonders of modern transportation. So the traveling salesperson problem says, okay, I need to sell my widgets to some person in each of these cities. What is the cheapest flight path? What is my cheapest itinerary? Going from A to B to C, is it from A to B to C to D to E, or should I go to E to B to C to A to D, right? Which of these flight paths are the cheapest, right? Right, I can even assume I'm starting out in one of the cities. It doesn't really matter. The point is that which of these paths to take, because I can hop from any one of these, is the cheapest? And the answer is, I really don't know. I can figure that out, though, but I'd have to check. What do I have to do? I have to check all the possibilities. Do I want to go to A? Do I want to go to from A to C first, or A to B, or A to D, or A to E? There's no way to know unless I write out all the possibilities. Now, how many possibilities are there? Well, if you've taken any combinatorics, there are 5 possibilities for your first city. Then there's 4 possibilities. Then 3 possibilities. Then 2 possibilities for your second choice, and then you are left only 1. Right? So you choose one city first, then another city, then another city, then another city. Right? And this should look familiar, right? This is equal to 5 factorial choices. Right? You essentially have 5 factorial choices on what you want to choose. It's a lot of choices to make, and that's 5 times 4. That's, I think, right? This should be about 120 choices, I think. Right? That's about 120 different choices that you have to explore. Right, is that right? Yeah, 6 times 4 is 24, times 5 is 120. Okay, so that's not too many for your computer to check, but generally we're not talking about a lone guy traveling around to 5 different cities. Generally we're talking about, like, routing some very complex network with maybe, 20 cities, and 20 factorial is a really big number, right? I mean, it's a really big number. Okay, so I will leave that there.